good electrical conductors are also usually pretty decent thermal conductors, namely metal. As an example, could I get a volunteer to come up here? Because that way it's not just me doing this, and you can get someone else's perspective on it. And all you would have to do is touch this plank of wood and then this piece of metal. Okay, thank you very much. So, we are all currently in this room touching the same temperature air, right? And no one's been in this room all night. Every object in this room has been getting the same temperature air all night until we came in here today. So, technically speaking, due to the 0th law of thermodynamics, this wood plank and this piece of metal should be the same temperature, correct? Okay. So, what I would like you to do, just take one hand each, put one hand on the plank of wood and one hand on that steel rod. Do you feel a temperature difference? Yeah. Okay, so what feels colder?
The steel.
Okay, and therefore the wood felt warmer? Mm-hmm. But why do you think that is if they should be at the same temperature? Sorry?
One absorbs more heat faster.
There we go. So, the thing about humans' ability to detect thermal energy is it's really bad. You don't feel temperature. You just feel thermal energy leaving you or entering you. Your nerve endings and your temperature response and your pain response is simply tied to thermal energy leaving or entering. You don't have an actual thermostat in your fingertips that says, yes, that's 25 Celsius. You just feel, I'm losing energy, ouch, or I'm gaining energy, ouch. So, even though both these things are at the same temperature, wood has a low, I'm going to skip a few tabs here, don't panic. Wood, this is a table of thermal conductivities. Higher numbers means more thermal energy passes through every single second. Wood, very low thermal conductivity. Not much thermal energy passes through wood every single second. But, one of those pipes is aluminum, so let's just look at aluminum. Wow, that's a lot of thermal energy passing through every single second. So even though they're the same temperature, with the wood, less thermal energy leaves your fingers every single second than with the aluminum. So the aluminum feels colder because all you can feel is that's more thermal energy leaving me. And so the type of material is what affects that. And so kind of a similar reason to, this also relates back to the example I gave with stepping on hot concrete on summer versus stepping on the grass. The concrete is at a higher temperature, but it also has a higher thermal energy transfer rate than the water in the grass. So this ties back into that also. And if we just look at some of these numbers here. Glass. Okay, here we go. So here's glass. Not a very high ratio, but it's higher than, say, the asbestos we used to use as thermal insulation. We don't anymore, but we used to. And notice, yeah, we lose more heat through glass than we do through asbestos. We lose even more through concrete, which is why we tend not to just have solid slab concrete exterior walls if you like living comfortably. Now, I realize we're at the end of the period, so I'm just going to point and explain these formulas, which I would like you to write down so that you at least have them to begin trying to use them. We'll cover examples with these on Tuesday. So, again, power is defined as change in energy over time. So the flow of thermal energy per unit time, that tells you the thermal power, the rate of energy exchange. That is proportional to, this symbol means proportional, so this does not equal this, they're simply proportional to each other. That is proportional to the surface area of the object times the temperature differential on either side divided by the length or depth of the object. And what that means is if, say your walls were this wide, so your walls were this thick, a thicker wall, that means that your wall is thicker. That means there's more area, there's more depth that thermal energy needs to pass through. So thicker walls means energy transfers more slowly. Notice the length here is proportional to the time. So more length, more time. The thicker your walls, the better insulated your house is, which again is why the thicker walls hold heat better than the thin glass. We also have surface area. So if I orient it like this, cold wind is hitting more surface area here, and therefore there's more area for thermal energy to transfer out. So smaller buildings hold their heat better than bigger ones. Notice if area is bigger, that corresponds to the thermal energy passing out. There's more space for thermal energy to leave. Which is why if you want to stay warm, you have to cover up your surface area with a jacket. Now the actual formula that we're going to use, some very smart people took all of this and combined it together to get this. So the rate of energy flow, the thermal power, equals K, which is these are the Ks, K represents this constant, times the surface area of the wall, times the temperature differential across the wall, divided by the depth of the wall. We will use this next time, just write it down for now, and I will see those who didn't do lab in lab today, and I hope you have a wonderful weekend. Please keep working on your homework. Chapter 10 is due on Sunday night. Chapter 11 will be due next Friday night, not today, next Friday night. And have a wonderful long weekend. Get some sleep. I know I will.
I'll meet you in there.
I will also be sending out the 11 slides to those who have asked for them. If you want them, just email me.
Me.
Okay. And I have about 4 names for people who asked before.
Is there any reason about this, like the last ones?
The only reason I wouldn't is I tend to keep modifying my slides as the week goes on, based on how far we get. I'll maybe add notes or add examples. So I can send you what I have at the start of the week. It's just that's usually different to what I have at the end.